Hello, everybody, and welcome to our presentation. My name is Ulasik, and I work at Zurich University of Applied Sciences. Together with my colleagues from our research group, as well as two external partners, Spinning Bytes and Propulsion Academy, we've executed recently a number of projects related to speech-to-text and diarization. Today, we'd like to share with you our observations we've collected so far. So let's start.
Speech-to-text insights.
7 things you should know about STT and diarization.
This is a perfect speech-to-text output that we see here. Let's see what processing steps were performed to give us this output. We'll discuss it on an example of a typical STT systems. There are various architectures. So on the STT side, the process starts with acoustic analysis of the signal. The signal is split into very small frames, and acoustic features of these frames are extracted and used by a pre-trained acoustic model, which maps them to sequences of phonemes. Then, by applying pronunciation dictionaries, these phoneme sequences are transcribed into words. Finally, a pre-trained language model is used to predict most probable sequence of words based on the context. On the diarization side, the diarization tries to answer the question who spoke when, and the process starts with speech detection. So it's about distinguishing between speech and non-speech in the signal. The signal is then segmented so that each segment contains speech of only one speaker. Then these segments are clustered. The number of speakers defined and the segments of speech produced by the same speaker are grouped together. As a result, we receive a sequence of short time segments labeled with speaker IDs. Some systems put these two outputs together and provide a sequence of words with speaker IDs. STT and diarization are challenging tasks. One of the reasons is the variability of speech. This is why it requires a lot of data to train a system. The same word can be pronounced differently by the same speaker, by different native speakers, and not mentioning different non-native speakers where the variability is even higher. Background noise makes speech recognition much harder, as well as parallel speech. Here you can see an example of 6 transcripts, hypotheses, produced by 6 different systems. At the top, in the first row, you see the manual transcript, the reference, and in the last column on the right, you see the error rates. These are the word error rates. Word error rate is a standard metric used for evaluating STT. It's calculated by counting the errors in the hypothesis divided by the number of words in the reference. Word error rate is used in almost all our evaluations for evaluating STT. For diarization, we use diarization error rate. I'll discuss it later. Okay, so let's see what is the first insight we like to share with you. For pre-trained models, commercial systems outperform open source systems. What was this observation based on? We took over 47 hours of speech coming from 9 English public corpora and transcribed them with 7 systems. For each system, we picked at least 2 models or parameter sets. And for each utterance and model, we calculated the word error rate. The heat map above shows you the results. The first four systems are commercial tools. These are the average word error rates of the best performing model of each system on all corpora. The last 3 systems are open source, and their average word error rate is 33.1. So the difference is quite high. And when looking at this heat map, one may say that these results are actually surprising, taking into consideration what we read in the literature. There we read about word error rates of 5% or even less. Well, the reason is that it's hard to name one single word error rate per system, As for the same system, error rates differ drastically across corpora and across different models. You can see it on the example above. These are average word error rates per corpus of the best performing system in our evaluation. On the left, word error rate of 4.43. On the right, 40.23. The reason is that the corpus on the left, ST, is very different from the AMI corpus. ST is read aloud speech with native speakers recorded in a quiet environment. AMI is a conversational speech corpus with spontaneous speech with non-native speakers recorded in a meeting room with background noise. And so this is why the difference is so high. We also observe the same for models within the same system, as you can see in the example below. And here is another observation resulting from model comparison within one system. Training a dedicated model may substantially improve the quality for a particular domain or speaking style. We could see this on the example of Caldi. Caldi, in our comparison, Caldi has the 6th position in our general comparison. But when we took only one model, Caldi Aspire, trained on spontaneous speech, Fisher corpus, and we evaluated it on spontaneous speech corpora, it ranked 4th and outperformed one of the commercial systems. So when selecting a system, it's crucial to consider what are the properties of the speech we want to transcribe with the system. And also we need to take into considerations what are the available models and parameters. And another thing worth keeping in mind when performing system selection is that high speech recognition quality does not imply a high quality of diarization. We performed an experiment on German data. Spinning Byte is working on a product for interview transcription for German language. And we are trying to figure out what would be the best system to integrate it in the product. We investigated the best performing systems from our STT evaluation. We took 60 German dialogues and performed diarization with these tools. Then we calculated average diarization error rate and segmentation F-score for each system. Diarization error rate is calculated by adding the duration of non-speech classified as speech, speech classified as non-speech, and the duration of speaker confusion, all divided by the total duration of the reference. And what we've discovered, the worst performing commercial ASR system, according to our STT evaluation, turned out to be the best diarization engine. We've seen before that the error rate for spontaneous speech is high. Another insight is related to this observation. Spontaneous speech poses a significant challenge for any ASR system. And the reason are properties of spontaneous speech. This is high level of disfluencies. The speaking rate is higher. There are often incomplete sentences. There is speaker noise. There is overlapping speech. And for these reasons, the quality deteriorates so much. But there is also another reason. When you look at the example below, you can see that the word error rate is 50% for every transcript. So on one hand, the disfluencies lead to misrecognitions, but also this example, and especially the first transcription in these examples, shows that word error rate may be too rigorous if your main concern is semantic accuracy. This observation led us to an experiment which is presented here. We wanted to investigate what would be the error rate if we ignored all errors which don't seem to be semantically relevant. We classified the following error types as semantically not relevant: word segmentation differences, stop words and filled pauses, misrecognitions, spelling differences, numbers spelling differences, abbreviations and contractions differences, and words with the same lemma. The definition is very liberal, but helped us understand the word error rate results better. The results you can see on the left in the charts, and the conclusions were that between 48 and 61% of all system errors are semantically irrelevant. For spontaneous speech, these numbers were even higher. The last insights we'd like to share with you is related to confidence score. We observed that word level confidence scores may be inaccurate, but after our experiments, we could also see that they can be improved with calibration and ensembling. So what we did, first we assigned all words into 3 groups. Words with high confidence score, which are correct. This is the blue group in the example above. Words with middle confidence score, where we are not confident, and words with low confidence score, which are incorrect. This is the red group. We set ourselves 2 goals. We wanted to achieve the highest possible precision for the blue and the red group, and we wanted to make these groups as large as possible, but without exceeding a certain precision threshold, which we set to 0.95. We tried out 2 methods, aggregation and calibration with aggregation. I will not go into the details of these methods. I'd just like to mention that we used inputs from 2 systems. So we used ensembling. And then we compared the results of 3 approaches. If we don't do anything, this is the violet line in the chart below. If we aggregate only, this is the blue line. Or if we calibrate and aggregate, this is the black line. And you can see in this chart that the highest precision was achieved with the 3rd method, around 0.99. And assuming we don't want the precision to exceed our threshold, 0.95, the highest recall was also achieved with the 3rd method. So this way we could make the confidence score more robust. We'll proceed with our experiments for improving the confidence score. We also want to apply ensembling for improving the transcripts themselves. So there is a number of interesting projects ahead of us. And in the meantime, we hope you found valuable the insights we've presented to you today. So thank you very much for your attention, and feel free to contact us for any questions or comments. Thank you.